I have some shocking news. We're starting electricity. Sorry, I just had to do that one. Now, electricity is one of nature's most fascinating phenomena. You'll see it in storm clouds in the form of lightning, and you'll also see it sparking on your pajamas. You've definitely interacted with it too, be it by charging your phone or laptop, or shocking your friends or siblings with static electricity in the winters. But all that aside, what is electricity at its core, and how does it work? We're gonna learn all of that in this unit. It'll be electrifying. Yeah, I know, I cringed on that one as well. It's okay. Alright, I want you to try this. Take a plastic ruler and rub it against a woolen cloth. When you do that, you'll see that it suddenly seems to be attracting small pieces of paper, almost as if it's a magnet. If only relationships were that simple. Anywho, now rub two plastic rulers of the same kind the same way. You'll see that they now seem to be repelling each other. In both of these cases, the effect doesn't last very long and it starts to wear out very quickly. What you're seeing in each of these cases is an electrostatic force that's attracting or repelling objects. It's basically static electricity. Let's summarize what's happening here. When you're rubbing these two objects together, you're basically messing around with their electrons, causing an excess here, a shortage there, and what this does is, it develops charges on those objects. And it's these charges that are causing those electrostatic forces. Just some context here. Atoms contain both electrons and protons. Now protons hold a positive charge and electrons hold a negative charge. An uncharged atom, that is a neutral atom, has an equal amount of both. So the negative charges of the electrons are cancelled out by the positive charges of the protons, creating a net neutral charge. Let's get back to our ruler example. When we rub the ruler against a woolen cloth, some of the outer electrons from the cloth basically get ripped off and stuck to the ruler. So now what happens is, the plastic ruler is covered with these extra electrons from the wool, and that's why it develops a negative charge, because now there's more electrons than protons. The woolen cloth, on the other hand, develops a positive charge because it's lost its outer electrons, and that's why it has more protons than electrons. So, a positive charge. Now, as the infamous saying in physics goes, opposites attract. These positive and negative charges can incur electrostatic forces, and in doing so, will attract their opposite charges. So, the negatively charged plastic ruler will attract the positively charged or neutral pieces of paper. But the story doesn't end here. They can also exhibit repelling forces, and that's exactly what they do when two like charges are brought together, as is the case with our two negatively charged plastic rulers. They start repelling each other. You can think of this whole scenario this way. Atoms don't like change. You've taken away their electrons or handed them more electrons, and that's change for them. They're going to do everything they can to get back to or close to their original state. So, if the ruler has electrons, it'll try to find a way to get rid of them. Now I already know that was probably really annoying, but you gotta deal with it. Back to the topic. Now a great instrument that can help detect these charges is called a gold leaf electroscope. It looks like this. You see that metal cap at the top? If a charged object comes in contact with the cap, some of its charges will transfer to the electroscope. And this is because electrons in metal can move freely about. And that makes it easier for charges to transfer through them. That's actually why metals are such good conductors. Now when this happens, the gold leaf and metal stem, both attached to the cap, gain the same type of charge. And since like charges repel, the leaf repels from the stem and rises. If another object with the same type of charge is brought near the electroscope, the leaf will rise even more, because this object also forces some charge on the cap to transfer to the leaf and stem, and that adds to the net charge. But these charges don't last forever. They're neutralized after a while. Remember how I said that the object will try to lose the electrons to another surface? Even if it doesn't find another surface, it will lose those electrons to its surroundings over time. And the same goes for objects with missing electrons. They slowly gain those electrons back from their surroundings. And this is especially prominent in metals. And that's because the atomic structure of metals allows electrons to move freely within them. And this is also exactly why metals can go through earthing, which is when electrons are able to flow between the metal and the earth. So, if a metal with a positive charge touches the ground, it will quickly attract electrons from the earth and neutralize itself. If it has a negative charge and it touches the ground, it will quickly repel the extra electrons, transferring them back into the earth and neutralizing itself. And that's why to get charged up, metals have to be isolated from the ground. Alright, you still with me? We've learned that charges can flow and that they can induce a force within a range around the charge. And this range is what we call an electric field. And in these fields, like charges repel and obviously opposite charges attract. But here's where things get more interesting. There's actually a way to show exactly how these charges interact. And not only that, you can also show what forces they can exert on each other. It's called field lines. What are field lines, you may ask? Well, good sir, field lines are basically the visual representation of how a charge exerts a force on another charge around it. Let's imagine you have a point positive charge, that is a positive charge represented by a single point. We can define the field lines around it by taking another point positive charge and placing it near the first charge. Just a quick point to note, for this to work, the second charge needs to be able to move freely. Once we've placed the charges, they react and move according to their forces. And we trace the path that the second charge takes. Because remember, this is the free moving charge. So this is the charge that will be moving. Now this gives us a field line for that specific area. And when we repeat this process for different areas around our point positive charge, we get a field pattern of how forces act around this charge. And the best part is, we can define these field lines and patterns for any set of charges, regardless of whether the source is a point or distributed across a plane. You will be surprised at how many things around you depend on the concept of electric fields, from air conditioners to soot removal devices called electrostatic precipitators. Precipitators. That's a fun word, precipitators. Anywho, in each case, a mesh is induced with an electric charge to produce an electric field. This field attracts and captures objects from the air that passes through it. So for example, for air conditioners, it's things like dust particles, while larger electrostatic precipitators in factories are used to remove harmful carbon and other gaseous materials from the factory exhaust. And that's just two examples. There's so many more uses for electric fields. But I think you've had enough for one video. We'll see you next time.